Okay, so good afternoon. Okay, so our topic for this week, no, is flow measurements. Makita ba ninyo yung flow measurements? Kita ninyo guys? As
Yes,
well
sir.
Yes,
as
sir.
the
Yes, sir.
as well as okay, as well as the YouTube, no, na the YouTube. Okay, so allow me to change my I'm going to share my window. Okay, so makita niyo si Flow. Kita niyo si Flow, no?
Sir.
Yes, sir.
Okay, so among the variables measurement, no? So naana ta sa flow. Okay, so saan na si flow, no? So in this uh, discussion, no, the concept of fluid velocity and flow, no, in its relation to pressure and viscosity, no, and other formulas, you know, used for flow measurements and instrumentation. Okay, measurement of fluid, no, flow is very important in industrial applications, no. Optimum performance of some equipment and operations requires specific flow rates. Okay, so these are the no, topics for this discussion. Reynolds number, the formula, the Bernoulli, and so on and so forth. Okay, so these are the basic terms, no? Velocity, laminar flow, turbulent flow, viscosity, Reynolds number, and so on and so forth. Okay, so defining velocity. So, basic naman yung velocity na, gibalikan naman natin eh. So, velocity is a measure of speed and direction of an object. When related to fluids, it is the rate of flow of fluid properties in a pipe. The speed of particles in a fluid flow varies across the flow. Where the fluid is in contact with the constraining walls, such as the boundary layer, the velocity of the liquid materials is virtually zero and the particles will have the maximum velocity at the center. Thus, an average rate of flow is used in flow calculations. So the units are maybe FPS or feet per second or FPM feet per minute or meters per second or centimeters per second and so on and so forth. Okay, so allow me to share to you my experience with this velocity meter or velocity current meter with the data logger and the brand is Infinity EM. Yun na siya. So, makita niyo si Kuan, si velocity meter, guys.
Yes, sir.
Okay, so kanang nasa left side, no? Left side of the hand, left hand side, mao na ang velocity meter, no, with data logger. So, magwonder mo, nga na may bukag diya. When I was still working in a project for BUST, no, particularly the familiar mo sa Project NOAA, naman na siya kanang succeeding na project with is the Philippine or PhilLiDAR, no, light detection ranging for kwan for flood hazard assessment, no. Dayon on the right side, mabasa na ninyo ba yung sanang sa right side na device or instrument? Basa ninyo? So kung mabasa ninyo, actually that is a water level logger, no? So nganong kinahanglan man ang water level ug ang velocity meter, no? Or velocity logger. Nga gibutang siya sa bukag, wala mo na tingala na. Dayon, butangan sa buka ang bukag gibutang ang bato. Ang sakay sunod ana na picture. So actually, gibutang siya sa, no? Gibutang siya sa ilalom sa river as much as possible. Okay? Nga naman, to determine the velocity, no, at a certain height, no, or depth sa imong river. Because of the project, so familiar mo sa Project NOAA, kuan mo na siya, sa mga, sige meaning sa NOAA. National Operation and Assessment of Hazards, so mo na siya. So, kani siya, murag partly sa kuan ni siya, sa Caraga na lugar, no. So, kinahanglan mabalaan ang kuan no, velocity sa imuhang kuan, water current, no, para magamit siya. Hello, kitsa nang nagturya, paki-mute sa mic. Okay, so kinahanglan ni siya na kuan na
Good afternoon, sir.
kinahanglan ni nakay pangutana bay? Wala. Okay, so kinahanglan ni siya na activity kay para ma-measure ang kuan no, ang water flow sa river. So particularly kanang kuan no, kanang mga dagko ano mga suba. Okay? Para ma-forecast siya in real time ang kuan ang ganang elevations of water which is related to flood hazard, no? So, ma-predict siya. But anyway, those were the days. Okay, so we go now to laminar flow. So, something laminar flow. So, laminar flow of a liquid occurs when its average velocity is comparatively low and the fluid particles tend to move smoothly in layers. No? The velocity of the particles across the liquid takes a parabolic shape. So, maraginana siya. Okay? So, the opposite of laminar flow is turbulent flow. No? Occurs when the flow velocity is high. So, gubot siya. In short, gubot. Gubot siya. Dili siya laminar. So, gubot. Okay? So, allow me to share ako ano, a tab. So, kanina na tab ako i-share.
Grammarly does more than catch errors.
Okay, so ako sa stop sharing. Ang ako i-sharing si laminar flow.
Sink faucet to demonstrate the difference between turbulent flow and laminar flow. First, laminar flow. I'll turn the faucet on. And if you notice the stream of water coming out, it's a very clear stream. In fact, if I put my finger behind the stream of water, you can clearly see the image of my finger through the water. This is laminar flow, where the water molecules are basically traveling in parallel with each other and not in a turbulent or mixing fashion. However, if I turn the water flow rate up, the flow stream becomes turbulent. You'll notice if I put my finger behind the water stream now, you see the image fluctuating. This is the turbulent.
Okay guys, so na-appreciate niyo the difference between laminar flow and turbulent flow. Maskin ko lang, no? Maski naara ka sa imuhang gripo, pwede ra na nimo siya pwede ra na nimo ma-demonstrate. Okay, so allow me to share again. Okay, so kita ba akong screen? Sometimes it's difficult in kung ano, mag-YouTube ka rin, mag-ano po. Hindi mo ko supported ang kuan video sa PowerPoint. But anyway, walay audio. Okay, so we go now to viscosity. So something viscosity sa Bisaya pa niyan sa kalapot, no? Viscosity is a property of gas or liquid that is measure of its resistance to motion flow. So kung lapot siya, taas yung viscosity. So a viscous liquid such as syrup, no? Sa maning syrup, ang tubig nimo butangan nimo og sugar, na viscous na siya, becomes higher viscosity than water. And water has a higher viscosity than air. Okay, so napay gitawag na viscosity dynamic, no? Can be measured in poise or centipoise, whereas a kinematic viscosity without a force is measured in stokes or centistokes. Okay, so typically viscosity of a liquid decreases as temperature increases. So mo na ilahang kuan, mo na ilahang uh, different na mga kuan, no? Equivalent, no? Dynamic viscosities and kinematic viscosities. Okay, so we go now to Reynolds number. R is a, no, is a derived relationships combining the density and viscosity of a liquid with its velocity of flow and the cross-sectional dimensions of flow. It takes the form R is equal to kana na formula. Okay, where B is the average velocity, D is the diameter of the pipe, rho is the density of the liquid, and sige niyo siya, kalimot ko ni mu ba ni? Absolute viscosity. Okay, so the flow patterns can be considered to be laminar, turbulent, or a combination of both. Okay, so ang nakadiscover ng Reynolds number si Osborne. No? So ang range sa kuano, makaingon ka that there is laminar flow if the Reynolds number is about 2,000 to 5,000. No? Okay? Pero kung less than or equal to 2,000, it is said to be laminar. Pag 2,000 to 5,000 can be between laminar, turbulent, or mixture. Okay? So, okay. Mga tong video the last time. But, pag beyond 5,000, the flow is said to be turbulent. Okay, so we go now to Bernoulli equation. So it's an equation for the flow based on the law of conservation of energy. States that the total energy of a fluid or gas at any point in a flow is equal to the total energy at all points in the flow. Okay? Okay, so flow rate. So it's the volume of fluid passing in a given point, no, in a given amount of time, and typically measured in, no, pwede siya GPM, no, gallons per minute, pwede pa cubic feet per minute, liters per minute, and so on and so forth. So these are the different conversion factors. So you can memorize or pwede po you can go ano, you can have a common uh, unit para ma-convert din mo siya. Okay, so on the other hand, total flow is the volume. Pag may nga total flow, pwede pa na nimo ignon na volumetric flow. Total flow is the volume, the liquid flowing over a period of time and is measured in gallons and so on and so forth. Okay. By the way, the energy losses, no, in the flowing fluids are caused by friction. So, pangutana guys, asa may mas bugnaw or tugnaw dahil maligo sa buntag. Kanang mag-agas imong gripo or katong stagnant water.
Stuck, sir.
Mas bugnaw ang stagnant, very good. No, mas bugnaw siya because wala may friction na generate. Kung magpaagas ka o gripo na may friction, so therefore relatively dili kayo bugnaw, no? Tugnaw gito. Kuan stagnant ang water. Okay? Very good. So we go now to the continuity equation. Okay? So maano siya, no? So familiar naman mo ani, this is just a review na alam na sa inyo fluid mechanics, no? Formula of flow rate is equals to the velocity times the cross-sectional area. Okay? So, kung inani po ng case, no, kanang nagamay kalit ang pipe, sometimes inana na siya, especially pag ang imuhang mga requirements is nga kulang, no? Kulang imo requirements magamay ang pipe, kasi dako siya imo gamay, then ang imuhang kuan pud siguro mga instrument, let's say flow meter, no? Maski dako unta to na flow meter ang gipalit, nya kay na short man, so gipagamay siya. So naay mga inanan mga cases, no? So therefore you apply this one equation. Kaning equation na no? Na siya. Velocity 1 is equal to area 1 is equal to velocity 2 area 2. Okay? Example, what is the flow rate through a pipe? No? Ang pipe na to is 9-inch diameter. If the average velocity is 5 feet per second. Okay? So, naman tayo formula sa Q, no? Velocity times area. So, therefore, mo na itong area. It's the area of the cross-sectional area of the pipe. It's circle siya. Okay? So, since diameter man given, you convert nito natin into feet. So, 9 divided by 12 is actually 3/4 or 0.75. So, this is the area of the circle. Then, this is now 5 feet per second or 5 FPS. So, therefore, masolve na din mo, i-convert din mo as required, no? Convert ba nimo to gallons per minute or gallons per second? Depende lang. Okay? So, that is now Q, the flow rate. Yung may pangutana, it's a simple ko naman, no? Linear na formula. Okay, so unsa mo panikpod? If a pipe goes from 9, so kanina gamay na, no? From 9 centimeter na imo na siyang 6, no? So given na ang velocity sa sa kaning fluid sa imong 9 centimeter, ang pangutana now is what is the velocity now of the fluid sa 6 centimeter. So you use this formula, okay? So kabalo naman mo ana, what is important is consistent mo sa unit, and you know that the pipe has a cross-sectional area of a circle. Okay? Okay, so we go now to mass flow, no? Rate or F. So related to the volume flow rate by Q. So, ano siya? So where F is the mass of the liquid flowing and the rho is the density of the liquid. So na iyang formula. So ma-modify na siya. Multiply na din siya of specific weight. Okay? So, dugang na ka og specific weight. Pag mass flow rate na ang ato ang ginastoryahan. Dili lang volume, no? But mass. So, kabalo man mo that relationship between mass and volume and density as well as a specific weight. Okay, so we gonna have the Bernoulli equation. So, si Kuan mo isa. Sige, ngalan niya. Kalimot ko sa first name ni Bernoulli. Okay, so inani, no? So this is now the Bernoulli equation. So let us say you have this vessel from point A to point B. So ano siya? So maning A ay B. So there is kinetic and static na energy involved. Okay, this is just a review. No? Okay, so this is just a review. Okay? So, obserbahan mo, asa man ang imuhang pressure. So, kaning involved o kaning no? Pressure. And by the way, these are all in heads, no? Or in height. Then the kinetic energy, morning involved with velocity. Then kanidang imuhang potential energy. So, mawara na sila kay. So the question now is, no, in an open tank, so nakakay kaning kuan, so tawag gani, kaning dispenser, water dispenser. Open tank man na siya, dili na siya pressurized. Okay, so in an open tank of water, what is now the flow velocity at point 3? So, So you use the Bernoulli's equation. So zero ang ato ang kinetic energy. Zero. Or rather at initially zero ang velocity. Okay. Pero once abrihan na nimo, poset na na siya kinetic energy. Okay? Okay, so point 3 has a dynamic pressure but no static pressure above 1 atmospheric. So therefore, P3 is equal to P1. Okay? Okay? So mga cancel out sila, no? So, saan nila nabilin? Saan nila nabilin, guys? So, actually, this is the same as free falling body. Yung kadumdum ba mo sa inyo ang free falling body sa physics? Okay? So, the velocity of opening the then yung water dispenser is actually lang. Same sa kaning free falling body na equation. So, mga dahil ang ang velocity. Okay. So, example, if height in this given figure, is 7.5. Namin din 7.5 na siya. What is the pressure at P2? At point 2 kanina rin. Assume that the areas at point 2 and point 3 are 0.48 square meter and 0.3 square meter respectively. Okay, so manotice din mo, mas dako gini siya, hindi magamay. So, the same ganiya, kabalo naman ta, di na nato i-derive yun na formula, no? Kabalo naman ta sa scenario. Okay, so just simply apply the formula. Okay, then, masolve na din mo ang katong is the final velocity. Ang pag-open mo sa imong kuan. So, ang masolve na din mo is now masolve mo. So, okay? So, masolve na din mo ang pressure which is 44.7 kilopascal. Okay? So, this is just a review. Okay? Okay, so due to some fittings, valves, elbows, mga bendings, mga teeth, in a pipe connection or system, na gitawag na losses, no? So, example is outlet losses. Okay? Napay gitawag na frictional losses. No? So, mao po niya ang empirical na formula. Okay? So, example, what is the head loss in a 2-inch diameter pipe? That is 120 feet long. The friction factor is 0.03 and the average velocity. Okay, so you just simply apply the formula. Okay. Fitting losses, no? Nga mag-fitting losses mangga kay sometimes nagsumpay mangga pipe, no? So naagi kay mga fitting na mga adapters na kinahanglan. So mao pa na yung empirical na formula. Okay, so what is the fluid is flowing at 4.5 feet per second through 1-inch fittings, no? As follows. 5 by 90 degrees elbow. Dahil tulo ka T, then isa ka gate valve and 12 couplings. So, because of this, interruption, no? Interruption sa imong straight pipe connection, supposedly, so there will be losses na incur. Okay? So, just apply the formula, no? Accordingly.
Sir, elbow man ang L, sir ba?
Ha? Oh,
Elbow
elbow.
ang pasabot.
Elbow.
Okay, sir.
L. Oh. Dili nimo butang dili mo magamit og letter na L kay confusing siya. That's why ang ihang gibutang diha L or elbow. 5 kabok elbows. Then 90 degrees kay na may mga elbow food na 45 degrees. Pero wag ko kita og 60 degrees. Ako ra kasagaran makita is 45 degrees and 90. But majority is ang 90 degrees. Okay? So dere pang samra nimo no. Pang samra na nimo si ang sabi ni Permero. 5 times 1.5. Okay, mano siya. Threaded elbow, 1 inch. Okay. Dayon, sunod. Tulo ka T. So, letter T na siya. Ang spelling, ginana lang kay. Kung letter T maguni mo, dili siya masabtan. So, bali, ang ganing L's, elbows, or L's and T's, kuha ni siya kanang sounds like lang. Dili rin siya maugid ang kanang itawag nila na kung ano. Okay, ang t-shirt, letter T man, so gituyo na siya para dili ka maglibog. Okay, para di siya misleading. Gituyo ang spelling niya. Okay, so 3 times, tulo man ka T. So 0.9, naman yung 0.9. Ito ra, threaded T. Ayun, plus isa ka gate bulb. Asa man gate bulb? Ito ra, threaded na gate bulb. Plus, 12 ka couplings. Sumpay-sumpay gina ni. So, pila man ng couplings. Gamay ra yung losses, no? 0.085. Okay? And so on and so forth. Okay? Okay. So, pag take into account na nimo ang mga fraction losses, fittings, and so forth, isamra nimo. Samra nimo diri. Okay? So, in terms of height na sila always. Okay, so, something form drag. Hindi kayo familiar sa form drag. Form drag is the impact force exerted on device protruding in a pipe due to the fluid flow. The force depends on the shape. Anyway, basta kuha na siya. Basta mao na iyang empirical na losses na formula. Okay, so substitute lang ninyo guys. Okay, so we go now to the flow measurements. No? Flow measurements are or particularly instrument, no? Flow measurement instruments. Okay? So flow measurements are normally indirect. So indirect na siya. Example is a differential pressure, no? Just to measure the flow rate. So far, the positive displacement flow meter and the turbine flow meter are one of the examples of direct flow measurement. Okay? So, kaning indirect, example lang is a differential pressure. Napay dagan example sa indirect. Okay, so, and flow measurements is also divided into flow rate, total flow or volumetric flow, and mass flow. Okay? So, tulo na sila ka category. Okay? So, it depends on the, kung unsa na application mo gamiton. Okay? Kinahanglan maka og flow rate lang or kinahanglan ba nimo ang total flow or volumetric or mass flow. Okay? So, depende na siya. Kasi example, this is a positive displacement, no? Flow meter. So, manotice ninyo na siya gear. Pag masulod siya diha, tuyok ni mo ang gear. Kaya define naman ang volume dere, no? Define naman ang volume. So that's why ma-measure na niya ang total flow or volumetric flow, no? Kuha niya ang total flow. So this positive displacement flow meter, ang principle niya is working like a filling and emptying the bucket. So kining mga space na nasa sulod niya mao na iyang filling, no, and emptying the bucket, ibalin niya diri sa imong discharge na na direction. Mao na siya ang concept na. Advantages is it is accurate, it is regardless of dili siya dependent sa imong viscosity, density, and temperature. There is no upstream and downstream requirements. Okay, suitable for both and high flow viscous fluid and smaller in size. Disadvantage, it has moving parts. So, wear and tear niya, so, madaot na gid siya kadugayan, no? Mura man siya, gears man siya, no? So, there is moving parts. Dayon creates pressure drop due to the resistance of these gears. No? Then, ang measurement niya, ah, ano, analog. Analog. Skip flow. Then, applications is potable water, batch processing, no? Sample of a video. Video ba? Video. Stop sharing.
My job is to make college easier because students have a lot to
Okay, I'm going to show the tab.
Positive displacement flow meters divide a flow stream into fixed, known volumes and count them to determine the total flow and flow rate. In a gear meter, the measurement chamber is created by the gaps formed between precision-engineered gear teeth and the meter's body. As liquid pushes against the gear teeth, the gears progress and isolate a volume of fluid. As liquid continues to enter the meter, the trapped portion of fluid is carried along by the gears until the fluid is released into the downstream side of the meter. This process repeats itself continuously. You will notice the meter is impervious to intermittent or start-stop flows and changes in viscosity. This is unique to positive displacement meters. One benefit to max meters is the high-resolution transmitter that uses a magnetic signal to report the movement of an internal shaft as opposed to counting the gear teeth. In the frequency version of our model G004, for example, this means as many as 500.
Okay, so I hope na appreciate din yung video. So going back to my window. Hindi man kita kung window. Tara. Okay, so mao na ang positive displacement. Then another direct, no? Direct type na measurement is the tawagan turbine flow meter sa rotating flow rate device, no? So nay familiar man mo ganang mutuyok, no? Mutuyok ang imong turbine. So it's mounted at the center and then mutuyok siya. Okay? Maskin gamay lang ang fluid or mapuno ang fluid as long na there is current flow, mutuyok siya. That's why it's flow rate measurement rather than, no, in comparison to kining ato ang kuan positive displacement flow meter, it's a total flow or volumetric flow. However, pwede man ma-convert ang flow rate into total flow or volumetric flow. Okay? So, kung maminaw mo ganiya, there's also a tendency that you can add Hall effect device or kaning magneto-resistive element. It's may familiar sa kaning fan sa kaning heatsink fan sa imong CPU. No, naana siya kuan Hall effect na sensor na para ma-measure niya ang RPM sa imong fan. The same is true with this kuan kaning turbine type. So in fact, kung gusto ganahan mo o ganing kung ano project sa inyong napay baligya sa Shopee, no? Turbine flow sensor. Basahon nimo ayay. Basahon nimo na siya gitawag na kanino 12 volts water flow sensor. Hall flow sensor. So therefore there is a Hall sensor or Hall effect. Okay? Dayon napa na code sa Arduino kung ganahan mo sa Arduino. Requires a code or a library. Okay? So example of application of kuan turbine flow is this kuan no kining sa tubig. Sa So, share na po na ako mga dynamic water. So, nakita nyo guys, no? So, mao ni ang usual sa kaning kuan no turbine type sa kaning ato ang tubig no. Kaning raw water na to or kaning kuan. Ang tawag ani potable water. So, na siya. Dahil yun mutuyok din dito sa kuan sa iyang meter na part sa iyang top view. Okay, so share na po nato ito ang slide window. Okay, so napay gitawag na turbine, no? Ay tanay gitawag ganing napay nani na type pareha ra principle ganiya din na nato i-play. Okay, so let's proceed no to kuan na indirect which is the differential pressure, no? Measurements can be made for flow rate, no? Determination when the fluid flows through a restriction and works on the principle of the Bernoulli's equation. So these restrictions could be orifice plate, a venturi tube, flow nozzle, and Dahl tube. Okay? So, mani sila. Yung CA, sabi siya, orifice type, plate, then ang pinaka-common is si venturi, then followed by si flow nozzle, then si Dahl tube. Okay, so take note, this is indirect type, no? Ganiya, direct type to. Karon indirect na ta. And since indirect man, it is using a pressure to measure the flow or technically the differential pressure. Okay, so naano po tayo video?
The most diverse substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas, or steam for energy transmission. The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity, and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow.
Okay, so those are the three na variations of restrictions. So show window. Para. Okay, so kay advantage sa to ang differential flow meter. Kaya advantage niya. No moving parts. Unlike atong direct type turbine o gatong positive displacement. Okay. Dion. Okay. So flexibility in terms of size na effect. Same sila, temperature, density, and electrical conductivity can operate in both directions. Ang disadvantage niya is, so because of the restriction, it causes pressure drop, no? Na magay restriction. This is a restriction type na na technology. So, nagi siya pressure drop losses. Then the installation cost is halos pare-pareha naman karon tanan. And within the range difficult to measure pulsating pulse flow. So dapat dili siya mag-utro-utro o impulsive ang iyang flow. Then difficult to measure low. Pag ubos pa ang imong flow rate, lisod pa siya i-measure. Okay, then the applications are suitable for both liquid and gas, bidirectional flow versus viscous chemical, gas, and oil. Okay? So, ganiya, na-mention ang Venturi tube. So, maano yung Venturi tube? No? Yan sa taas. Na siya small, na siya narrow na. Okay. Then, this is the the flow nozzle. Okay, it compromises the cost of accuracy between orifice and venturi. It is not normally used for suspended particles, yun na yung mga suspended solids. Okay. So, usually for boilers, no? Mga ni kasagaran ginagamit. Okay. Dal tube has the lowest insertion loss, but it's not suitable for slurries. So, may mga slurry na to. Okay. Then, so these are the summary, no, among the this differential pressure na technology. So the orifice is the simplest and the cheapest and the easiest to replace, least accurate, more subject to damage and erosion, and has the highest loss. Then venturi tube is more difficult to replace, most expensive, most accurate, has a high tolerance to damage and erosion, and lowest losses among the tubes. Then the flow nozzle is in between, between the dull tube. That advantage of having the lowest insertion loss, but cannot be good with slurries. So we have a speaker before, no, uh, based on his experience, ang pinaka-accurate in terms of type na measurement, no, or flow meter is ang ganing differential. Pinaka-accurate yun siya yung differential. Wala niya ang mga disadvantages. Okay, so we go now to flow rate by electromagnetism. Okay, so or what is known as the magnetic or magmeters or mag flow meters. It works on the principle of Faraday's law. So kung familiar mo sa Faraday's law, no, the induced voltage is directly proportional to the magnetic flux na generated. Pareha na sa principle sa transformer o sa induction motor. Faraday's law nito. Disadvantage lang niya, it can only work on conductive liquids. So, pwede rin sa tubig or coconut water. Hindi na siya pwede sa distilled water. Okay, take note. Distilled water is not conductive. Okay, wala man siya electrolytes, wala siya impurities. In fact, dili ka makurintiyan, no? Kana sa distilled water na wires, no, i-plug them sa 20, then as long na distilled siya, wala impurities, di ka makurintiyan. That's why distilled water is not considered conductive liquid. Okay, so kanang mga raw water, any form of water na na electrolytes, no, is conductive liquid. Okay, so this device consists of 2 electrodes, no? So kita ni mo diri sa taas, no, so, positive and negative, no, siya. So mas better ni siya i-demonstrate through a video. Maayong video kay pag-explain. Okay, click magnetic flow meter or mag flow meter. Okay, asa naman to?
To realize automotive change, we support electrification and in-vehicle networks for automated driving.
And how it works. Magnetic flow meter is an instrument which uses a magnetic field to measure the volume of fluid which is flowing through a pipe in a set period of time. A magnetic flow meter is also known as electromagnetic flow meter or magmeter. They do not have any moving parts. They are obstruction-less, cost-effective, bidirectional and provide highly accurate volumetric flow measurement. They are suitable for wide range of pipe sizes and can be used to measure flow rate of only conductive fluids. Parts of magnetic flow meter. Electromagnetic flow meters consist of a sensor and transmitter that together works to measure flow. The sensor is placed in a pipeline and measures the induced voltage generated by the fluid as it flows through a magnetic field. The transmitter takes this voltage generated by the sensor and converts this voltage into a flow measurement and transmits that flow measurement to a control system. Magnetic flow meter typically consists of two electromagnetic coils that are mounted on opposite sides of a non-magnetic flow tube. These electromagnetic coils produce the magnetic field, and this magnetic field has to permeate the process liquid through the flow tube wall. And due to this reason, the flow tube should not have magnetic properties. So non-ferromagnetic flow tube is used. The inside of the measuring tube is lined by an insulating material such as rubber, neoprene, etc., which is resistant to the properties of the fluid, and the liner should be non-conductive. Two electrodes are fitted inside the tube to detect the voltage generated by the conducting fluid. Operating principle of magnetic flow meter. The operation of a magnetic flow meter or magmeter is based on Faraday's law of induction. Faraday's law of induction states that the voltage induced across any conductor as it moves at right angles through a magnetic field is proportional to the velocity of that conductor. In magnetic flow meters, electrically conductive flowing fluid works as the conductor. So according to Faraday's law, when a conductive fluid flows through a magnetic field, it generates voltage. When the conductive fluid is flowing more quickly, more voltage is generated. The voltage generated is proportional to the velocity of the flowing fluid. Working of a magnetic flow meter. Consider that we have installed a magnetic flow meter to measure volume of a conductive fluid flowing through a pipe. A conductive fluid contains positively and negatively charged ions. The flow of these ions conduct electricity through the conductive fluid. These charged particles are evenly distributed in the fluid. When a current is applied to the electromagnetic coil, they generate a constant magnetic field across the cross-sectional area of the flow tube. This magnetic field applies a force to the charged particles, and as a result, the positively and negatively charged particles in the fluid get separated and collect on the opposite sides of the flow tube. Now an electrical voltage is formed. This electrical voltage is picked up by the electrodes and is sent to a transmitter which is either mounted on the flow meter or connected remotely. This induced voltage will be proportional to the velocity of the fluid in the pipe. Knowing the velocity and dimension of the pipe's cross-section, flow volume can be calculated. By this, we come to the end of this video. If you like this video,
Okay, so mas maayos siya explain, no? Kumpara sa kuha. Okay, so allow me to show again my window. Okay, so these are the advantages, no? It's linear over wide range. As long na kuha, no? Water ang involved, mas nindot yun yung kuha, magmeter. Kay kuha man siya. Kaya walay moving parts and it is highly accurate. Okay. So, ano yan, suitable for viscous and slurry. And ang disadvantage lang niya, dili siya pwede pag dili siya conductive ang fluids. Conductive fluids lang yun. And of course, mahal siya. So since we're talking about conductive fluids, that's why it's usable, suitable for potable water, raw water. Wala gibutang dia distilled water ha. Kaya ang distilled water kay wala man na impurities. Is the impurities that cause the conductivity sa water. As well as the coconut water or dirty or slurry liquids. Wastewater, okay? Yan ang yung mga wastewater treatment plant. So, importante na pulp and paper industries. Okay? Okay, nagbalik-balik. Okay, so we go now to, mana naman ta sa kwa, no? Flow rate. Dahil mana na punta itong volumetric or total flow rate. So we go now to the mass flow rate. So a mass flow meter, also known as the inertial flow meter, is a device that measures mass flow rate of a fluid traveling through a tube. The mass flow rate is the mass of the fluid traveling past at a fixed point per unit of time. Okay? So, ang unit niya could be cubic meters per second, kilograms per second, So mass gid siya, ang mass. Okay? So actually wala ko kakitaan ni na ano, I don't know, dili na siguro ni kay gagamiton unless you require siya of accuracy. This is a mass flowmeter using Coriolis. This is Coriolis type of kitaan. Okay? Ang amo ra na gamit, no, it's actually the vortex flowmeter. A vortex flowmeter is typically used for volumetric flow rate, but since majority of the vortex flowmeter dagana siya pakapin, siya temperature sensor, na siya pressure sensor, no, pwede na dahil mo ma-measure, no, ma-convert, no, na siya computer pod, pwede na i-convert na dahil into mass flow rate. So bigyan na punta. Okay, so stop sharing. Share na ako ang katong flow.
Flow measurements are essential to running a plant efficiently and safely. There is an array of flow technologies available to make these measurements, including the Vortex flow meter. Vortex meters offer many advantages for flow measurement, including easy installation without impulse lines, no moving parts to maintain or repair, less leak potential, and a wide flow turndown range. Vortex flow meters are comprised of a meter body, a sensor, and a transmitter, which together measure the volumetric flow rate. Within a vortex flow meter, an obstruction in the flow path, often referred to as a sheddar bar, causes process fluid to separate and form areas of alternating differential pressure, known as vortices, around the backside of the sheddar bar. These vortices then cause a small sensing element either behind or within the sheddar bar to oscillate back and forth at a specific frequency. The velocity of the working fluid is directly proportional to the frequency of the vortices generated by the sheddar bar's unique geometry. Using the known cross-sectional area of the pipe, volumetric flow can be calculated. This flow principle is referred to as the von Karman effect, a proportionality constant which relates the frequency of the alternating vortices to flow rate. The calibration constant is formed in a flow lab by measuring the amount of pulses that are generated per 1 unit of volumetric flow. This calibration constant is accurate over a wide operating range of Reynolds numbers. Because vortices must form in order for the vortex technology to pick up a signal, an adequate ratio of inertial forces to viscous forces must exist. If not, the meter will read no flow when the fluid is flowing. Once a mechanical signal has been formed by the vortices passing by the sheddar bar, a sensing element takes the mechanical motion generated by the flexure and converts it into an electrical signal. This electrical signal is then passed from the sensing element through a circuit up to the electronics board stack, where it is then processed and turned into a quantifiable velocity reading. This signal is then outputted to the vortex's local display and out to the control system. Vortex flow meters are well suited for a wide range of applications and can accommodate liquids, gases, and steam while being able to withstand high process pressures and temperatures. Vortex flow meters are also a two-wire device, making them efficient with respect to power consumption. Vortex meters are available in a variety of meter body configurations and multivariable capabilities, allowing for compensated mass flow readings. By measuring additional variables such as pressure or temperature, along with the volumetric flow reading, fluctuations in density can be accounted for to provide an accurate mass flow reading. Compensated vortex flow meters can prove to be especially useful in saturated and superheated steam applications, along with liquid applications in which a fluid is nearing its saturation point. Low flow cutoffs in minimal measurable flows can pose an issue to vortex technology. One solution to this limitation is utilizing a vortex flow meter known as a reducer. This configuration decreases the cross-sectional area of the meter body by 1 line size, yielding a higher velocity through the pipe. With a higher velocity passing by the sheddar bar, lower flow rates can be accurately measured. Reducer vortex flow meters use the same face-to-face dimensions as standard flanged vortex meters, which decreases costs by eliminating the need for field-installed piping reductions. For chemical plants and refineries, safety instrumented systems, or SIS applications, are critical to keep a plant running smoothly and safely. Dual and quad vortex flow meter configurations exist to accommodate these type of applications by providing redundant, independent sensors and electronics. This provides redundancy for uncommon modes of failures and helps to protect against spurious trips that these plants may experience. Emerson's Rosemount Vortex flow meters offer unmatched reliability using an all-welded, all-cast design with online removable sensors for enhanced safety and maximum process availability. Emerson also offers the widest selection of materials to provide a tailored solution for any process or utility challenge.
Okay, so may explain ang YouTube. Okay, so window. Okay, doon na ta mahuman. Okay, so there are also other flow measuring devices. Dili na kayo ni siya. Wala na ko idea kung di ka exist ko ni sila. Kamo na labasa ni. Okay? Okay, so another thing, this is ultrasonic, So, ultrasonic flow meter works in the principle of Doppler effect. Kung kakita mo nga ng sakyanan niya sa taas, dagan-dagan, magkana sa inyo ang display. It is what is known as Doppler effect. The Doppler effect is the change in frequency of a wave in relation to the observer who is moving relative to the wave source. Okay? So, inana ang installation sa ultrasonic flow meter. Okay? Dili na nato ni i-play kamo na play ha. Okay, doon lang ta alas 6. Dayon so far here in the Northern Mindanao wala ko kadungog na maligya og ultrasonic flow meter. Okay, so we go now to the installation guidelines of flow meter. Sa inyo na-obserbahan guys, pag mag-install ka of flow meter, gitawag na 10D, 5D. Sa uban, gitawag niya na 5D, 2D, or 3D. Pero, sa akong na-recall, based on the manual, magbasa gid ba nag-manual, Hindi sa manual, basahan yung manual. But, this is most common, the 10D, 5D. May pasabot sa 10D, 5D. Sabutan na, 10 times the diameter of 5 times the diameter. So, ang upstream nimo, anang pasulod ang imong product, is dapat 10 times the diameter ang length niya, na dili siya maputol, dili siya mabaliko. So, 10 times the diameter, straight yun siya. Hindi siya magliko-liko. But sa imong downstream, pwede ra 5 times the diameter. Okay, may pasabot sa 10D, 5D. Ang uban na ni wala kabalo, dili gabasa og manual, laman ni sa manual, diretso ra install. Ang ending dili kay siya accurate. Dili accurate ang imong flow meter na measurement. Okay, so installation, kuha ni siya murag na sa simulation.
To realize automotive case, we support electrification and in-vehicle networks for automated driving. EDK supports the realization of case. We offer common mode filters and small size varistors for next generation in-vehicle.
Digid kalimtan ang gasket pag kay flange na connection. Dayon di pagkalimtan ang mga washers, Kung wala magaling na lock washer, plain washer pwede ra. So man akong gingon na 10D, na 10 times the diameter of 5 times the diameter. Okay, so reminder sa direction. Okay, as long na straight ang 10D of 5D, so pwede na tayong no? Mag-elbow or bend. Okay, so even ganing mga connections, appeal to siya, mga connectors, mga bulbs. And another thing is namin gitawag na batch type, kanang by batch bitaw na volumetric na requirement. So gina-program ang ato flow-meter. So this is just an example to demonstrate or to simulate how to program the flow-meter accordingly. Tama ng batching, ganang by batch siya. Pwede mo i-set ang batch. Then for another batch, pwede mo i-set ang batch count. Okay, so at least natin ano, simulation sa kilometers. So let's continue. Hapit na ta mahuman. Murag ay di mao ko na share. Kanina yung isa. Okay. And murag man naman siguro yung last calibration, wala naman siguro. Okay, so for the calibration, video lang yapon.
Ngayon, may new Susi the acrylic. Kaya sa mga kinasal, Susi ihaw sarap. Take out o delivery.
Ako yung inaasa.
In this lesson, we are going to discuss differential pressure transmitters. Simply put, a differential pressure transmitter is a device that measures two opposing pressures in a pipe or vessel. In the first video of this two-part series, we showed you how a differential pressure transmitter is used to measure the flow rate. You can find the link to this video in the description. This second part of our series will take you through the process of checking the output accuracy of a differential pressure flow transmitter and show you how to recalibrate it if necessary. If you haven't already done so, you might want to review two of our other videos, Differential Pressure Transmitter Explained and What is Sensor Calibration and Why is it Important? You can find the links to these videos in the description. In this video, we are going to describe how to correctly and safely remove a differential pressure flow transmitter from service, go through the steps involved in calibrating a differential pressure flow transmitter, and describe how to correctly and safely return a differential pressure flow transmitter to service. The transmitter must be removed from service before any checks or calibration can be performed. Let's go through the following steps. Close the low pressure block valve, open the equalizing valve, close the high pressure block valve. Okay. Let's go through the steps involved in checking and calibrating a differential pressure flow transmitter that has a separate square root extractor. Here's our situation. We have a flow system that will create a differential pressure of 200 inches of water column across an orifice at a flow rate of 50 gallons per minute. In our example, we are using a non-SI pressure unit called inches of water column. Inches of water column is one of several recognized pressure units and is very common in North America. The flow transmitter connected across the orifice produces a current output of 4 milliamps at 0 gallons per minute and 20 milliamps at 50 gallons per minute. We need to check and recalibrate if necessary. We are going to ignore the square root extractor for now, as we will be looking at the output current from the flow transmitter. The first thing we need is a calibration chart or table. A table like this or similar is usually kept on file at your place of work. This table is important from a calibration perspective, as it indicates what we need to apply to the transmitter and what the expected current output will be. Here's the calibration setup. The scissor-type hand pump with a digital pressure readout is connected to the high-pressure side of the transmitter. There are several different types of pressure sources used in the industry. Note that the low-pressure side of the transmitter is vented to the atmosphere. A digital multimeter set to measure current is connected in series with the transmitter and the 24-volt power supply. From the table, we can see that if we set the hand pump input pressure to 50 inches of water column, our multimeter should read 8 milliamps. Okay, now we've seen how the calibration table will work for us. We've got the transmitter all set up. Let's do some testing. First of all, we're going to check to see if the transmitter needs to be adjusted. We begin by applying the desired pressure input values from the calibration table to the high input on the flow transmitter and record the output current measured for each input value. If the output currents measured are outside of the acceptable ranges as established by your company, then the transmitter must be recalibrated using the zero and span adjustments. We perform the actual calibration using the zero and span adjustments on the transmitter. Apply the 0% input pressure value, which for us is 0 inches water column, to the transmitter and adjust the 0 until we get an output current of 4 milliamps. Apply the 100% input pressure value, which for us is 200 inches water column, to the transmitter and adjust the span until we get an output current of 20 milliamps. Repeat the steps until adjustments are no longer required. Now that you've recalibrated, it's a good idea to apply all of the values from the calibration table and record the corresponding output current values. Let's return the transmitter to service now that it's been calibrated. Begin with all valves closed. Open the equalizing valve. Open the high-pressure block valve slowly. Close the equalizing valve. Open the low-pressure block valve. Remember, we ignored the square root extractor when we calibrated the transmitter. Let's connect the square root extractor to the output of the transmitter and see what happens. We now have a linear and directly proportional relationship between the flow rate and the current output of the square root extractor. Perfect! That's exactly what our PLC or DCS needs to see. The math is a bit complicated, but let's try an example. When we have a 50% flow rate of 25 gallons per minute, the square root extractor output is 12 milliamps, or 50% as well. But the flow transmitter output is 8 milliamps, or 25%. How do we convert 8 milliamps to 12 milliamps? Very simply, the square root extractor will ensure that its output is the square root of its input. The square root of 25% is 50%. Try the math on a calculator. So with a flow transmitter output current of 8 milliamps, the square root extractor will produce an output current of 12 milliamps. Let's review what we've discussed. Before calibration, a transmitter must be removed from service by closing the low-pressure block valve first, then opening the equalizing valve second, and finally, closing the high-pressure block valve. Checking and calibrating the transmitter is completed by using values found in a calibration table or chart kept on site. The zero and span adjustments are used to obtain a specific current output range for a 0% and a 100% differential pressure input. After calibration, a transmitter is returned to service by opening the equalizing valve first, then opening the high-pressure block valve second, followed by closing the equalization valve, and finally, opening the low-pressure block valve. Be sure to download the RealPARS app.
Okay, that concludes our discussion, no? O, nasayos na gid. Okay, so nay pangutana guys. Ang uban nakatulog na ba? Katulog na?
Wala na, sir.
Wala,
Thank you,
sir.
sir.
Okay, mag-selfie sa tabi, selfie para print screen. Sige daw, be. One. Let's wait for others. Okay. 1, 2, 3. Bang. Napa? Again, bang. Okay na.